Advanced Financial Modeling, Topic 1, Asset Risk and Return. Learning Objective 5. In this one, we're going to estimate asset volatility using sample standard deviation and EWMA, volatility, exponentially weighted moving average. So when you choose an asset to put in a portfolio, this involves making a trade-off between risk and return. We've shown that CAPM and FinMod French are models to estimate the expected, required, or mean future returns. And we're going to define risk as the chance that that actual return deviates from the expected value. Standard deviation is a common measure of how returns deviate from their expected or mean values. And let's talk about this standard deviation and distributions in nature. If we graph enough data in nature, like the heights of women, the height of adult men, birth weight of children, and so on, what you find is many of them have a very similar distribution or shape. And that is, it's a single peak. We'll call that central tendency, the mean, and a symmetric distribution around the central tendency. And it seems to have kind of a bell-shaped curve. Got steep and then flattens out at the bottom. So if we collect enough data, and they've been doing this for hundreds of years, you find this normal distribution of things, primarily in nature. I tried to do that using snowfall in Philadelphia. I did get a bit of a single peak, but it was anything but symmetric. It seemed to have a really fat right tail. It's kind of an odd-shaped bell. All right, so this is what we call a normal distribution. That's just a normal distribution of things we find in nature. And if we start applying this to stock returns, so if you take a histogram of daily stock returns of these 6 assets, what you find is there also seems to be a central tendency, single peak. Kind of looks like a bell, but not really. You can see this one has a bit of a fat right tail. This one has a bit of a fat left tail. But we apply this concept of distributions in nature to stocks because there's been this, century or more development of mathematics and geometry around this bell-shaped curve that allows us to make different estimates. So again, so we're going to call this the normal distribution. You can also call it a bell curve, or you can call it a Gaussian distribution. So if you assume that stock returns, or all asset returns in general, are normally distributed as a computational shortcut, then you can fully describe the distribution of returns by simply having two metrics. The mean, which is the center of the bell, and the standard deviation, which is the thickness of the bell. Standard deviation is the square root of variance, and that's our measure of dispersion around the mean, the thickness of the bell. So that doesn't really help me out if I say standard deviation is the square root of variance, because we haven't defined variance. Variance is the average square deviation from the mean. So here's our formula for standard deviation and variance. Standard deviation, we're going to always use the Greek letter sigma, is equal to square root of variance. Variance you can think of as sigma squared. And variance is what this is. It's the average squared deviation from the mean. So say you had 100 observations of historical stock returns. Take the historical average, we'll call that mu, historical average of, say, 100 days of returns. And then what we do is we want to calculate the variance. Take 100 times, do this. Take the return on the first period minus the mean, square it, divide by 100. Return on the second period minus the mean, square it, divide by 100. So you can see what you're doing is you're taking an average square deviation from the mean. Now, why do we square it? Because if we didn't, by definition, the value would be 0. So we square it by to make sure that we have non-negative values and the average doesn't turn out to be 0. Okay. So here are a couple normal distribution functions in Excel. One is called norm est dist. So if you put in norm est dist and then plug in something called a z value, it'll give you a number, say 84%. So let's see what I did here. I did norm est dist, and where this says z, I put in a 1. And if you want to see this in a spreadsheet, you can just quickly jump over and go to normal dist here. All I did is I typed in this function, norm est dist, and the first parameter I put in was z, which is 1. And it returns 84%. So what does this function do? It's assuming a normal distribution, bell-shaped curve, and it's telling you, or your parameter you're inputting is z. So one way I think of interpreting this z is the number of standard deviations from the mean. So if you say z of 1 standard deviation above the mean, so we'll define this here, we'll define this here as our mean. And if it's 1 standard deviation above the mean, this is telling me in my normal curve, one standard deviation above the mean, it's going to give me the area to the left of that 1 standard deviation above the mean. So the area to the left of 1 standard deviation mean under this normal curve is 84%. Another interpretation of the area is a probability. What's the probability of having a mean plus 1 standard deviation or less? And that answer is 84%. If you take 1 minus that function, you get 15%. And what that's given me is the probability of having greater than a mean plus 1 standard deviation. So this is giving me 15%. Okay, so this is one function called norm est dist. If I use norm s inv, I can do the inverse of this function. In other words, I could put in the 84%. Remember I said there's 84% of the values are less than this standard deviation above the mean. Well, in this function, norm s inverse, and I type in 84%, it'll tell me that it's 1 standard deviation. Then the last function I'm writing in here is I'm taking 2 times norm est dist of the z. And we'll look at this in the spreadsheet so you can see exactly what I'm doing. I'm taking 2 times norm est dist of z and then subtracting 1. And so what does that give me? Well, if I put in a z of 2, a z of 2, what it's telling me is the area plus or minus 2 standard deviations from the mean. Minus 1 standard deviation from the mean, minus 2 standard deviations, plus 2 standard deviations. It tells me you should be 95% confident that if an asset is normally distributed with a mean mu and a standard deviation sigma, that you're 95% confident that any given return will be plus or minus 2 standard deviations. You're 68% confident plus or minus 1 standard deviation. 99.73% of the values should fall between plus 3 and minus 3 standard deviations from the mean. So these are useful functions in Excel that allow you to estimate normal distribution probabilities. Before we move on and start using standard deviation and normal distributions, like it's the only thing finance, or it's the only risk measure in finance, I want to make you weary of something. We are simply assuming normal distributions, and as a first approximation, asset returns tend to have that normal bell-shaped curve. However, it's not exactly true. All right, not all variables in nature or social factors like stock prices or stock returns are normally distributed. So just be careful. This is a computational shortcut. This is not the true distribution of stock returns. So risks are probably a little greater than what you would estimate using normal distributions. And I can talk about this in class. This will be a teaser in class. Okay, so let's just do some calculations. In Excel, we're going to use the var to calculate variance or var.s to calculate variance. And these are sample variances. Since we're always dealing with not a full population of asset returns or prices, we'll use the sample variance. The sample standard deviation, you just type in STDEV or STEV.s. So we're going to use these to calculate standard deviation. So let's go ahead and calculate monthly standard deviation and monthly variance for our data set. So I'm going to go back to topic 1, where it says 10-year standardized sample variance. I'm going to say equals var .s. I didn't need that capital there. And just be careful with this spreadsheet. I just need to go to the place where I have the returns. And if I go down here, these are monthly returns. Don't get the excess returns. I'm going to click on the first one and hit Control-Shift down, close the bracket. So that is the monthly variance. And if I calculate equals STDEV dot S for sample, and again I can go down here and grab the capital 1 returns, Control-Shift down, close the bracket. These are monthly variance and monthly standard deviation. However, in finance, we generally always take percentages and annualize them. So to annualize a variance, you multiply times, and this is a monthly data, so I multiply times time. However, to calculate standard deviation, remember we had to take the square root of variance, so you can't just multiply times time. You need to multiply times the square root of time to scale the standard deviation from monthly to annual. So there we go. That's my sample variance. That's my sample standard deviation. I can now copy this across. All right, so there we go. Looks like the riskiest asset over that period was Tesla. Also had the greatest return, I believe, right? Yes, it did. Had a 44% return with a 61% volatility. Note, if you want to go from annual standard deviation to daily standard deviation, you would divide by the square root of time, not multiply, if you're going to go to a smaller increment of time. And for daily returns, again, we'll probably use the 252 trading days per year. So if you had a daily standard deviation and you wanted an annual number, you'd multiply times the square root of 252. And if you had an annual number and you wanted a daily, you would divide by the square root of 252. All right, the last thing I'm going to do in this topic is talk about something called EWMA volatility. So before we talk about that more, I want to first redefine standard deviation. Standard deviation is the square root of variance. Variance is the sum of the square deviations from the mean, or it's the average square deviation from the mean. So you can write that as the sum from I equal 1 to n. Again, my example earlier, there's 1,000 observations or returns. I would take the return in the first period minus the mean return, square it, and multiply each one of those by 1 over 1,000. Just take a simple average. So standard deviation is the square root of variance. That's what the square root is. Variance is just the average squared deviation from the mean. So why do we want a new measure of volatility? Well, research has shown, empirical research of historical returns has shown that volatility is autocorrelated. We also say, we can say there's volatility clustering. In other words, when there's a lot of volatility in the market versus a long-term average standard deviation for a particular stock return, it tends to stay high, and if times are calm, they tend to stay calm before staying a little bit more calm before returning to average. So volatilities are autocorrelated. They're correlated with themselves. If yesterday was a big move, it's a little more likely that today is going to be a big move. Exponentially weighted moving average volatility, or EWMA, is a volatility estimate that weighs the more recent data more heavily when computing the volatility. So if I had, say, 100 days or 1,000 days, I'm not going to weigh every day 1 over 100 or 1 over 1,000. I'm going to weigh yesterday more than the day before, more than the day before. So we believe there's more information, more predictive power into what the future volatility is going to be. So I'm going to start with this formula. And what I'm going to do is I just want to replace this, think of it as a vector of weights, which in this case is just 1 over the number of observations, with this vector of weights. All right, this is where I usually scare people, but don't be scared. This isn't that hard. All we're doing is taking our simple variance formula. Again, let's just pretend there's 100 observations. Instead of taking return in any given day minus the mean squared times 1 over 100, each day getting the same weight, I'm going to replace that vector of weights with this vector of weights. All right, I'll say it out loud, then we'll explain it. That vector of weights is equal to the sum from I equal 1 to n, say 100 observations from 1 to 100, 1 minus lambda times lambda to the I minus 1 over the sum of all those factors. And then use that to weigh each period's squared deviation from the mean. At this point, it's probably best to jump to the spreadsheet. I'll just define lambda here as the Greek letter lambda as a mathematical constant, usually between 0.9 and 0.99. So let us go to the spreadsheet. All right, all I'm trying to do is replace this measure of volatility, 31.52%, the standard deviation. I want to measure that gives me a standard deviation, but it weighs what's been happening more recently higher. So I'm going to go down here. I have a little section set up here called EWMA. And the first thing I did is I just numbered my spreadsheet from the first observation to the 117th observation. So these are the observations of returns historically for, say, Capital One and the rest of the stocks. And now what I want to do is I want to build a set of weights to weigh. This one is yesterday, the last month. This is the month before. This is 3 months ago, 4 months ago, 5 months ago. So I want a set of weights that gets smaller, but then adds up to 100%. I'm going to define my lambda here. Notice I have a named range of L. That's going to make life a little bit easier. My lambda is 0.98. So my formula, which I've written in here, 1 minus lambda times lambda to the I minus 1 power, where I is the period. I'm going to say equals 1 minus lambda, which is just L, times lambda to the power of I, which is period, minus 1. Okay. 1 minus 0.8 times 0.8 to the 1 minus 1, which gives me 2%. I'm going to copy that down. Notice how you can think of these as weights. Notice they're getting smaller. If I graphed them, they'd be getting smaller exponentially fast. In other words, if I were to graph this column, you'd see that they go down like this. The weights go down really quickly. All right, here's the problem with these weights. If I just did the 1 minus lambda times lambda to the I minus 1, notice I double-click just to copy the series to the bottom. That always works if there's a column to the left that's already filled in. All right, so I have this. Notice when I sum the weights up, they only add up to 90%. That's bad. I need my weights to add up to 100. Otherwise, they're not. One good characteristic of a set of weights is they sum up to 100. So here's what we're going to do. The actual weight I'm going to use is that 2% divided by the sum. This is just the sum of the weights. So I'll just take the 2% divided by the sum, anchor the sum, copy that down. Now these are the weights I'm going to apply to calculate variance. So back to the formula. All we've done so far is we calculate the 1 minus lambda times lambda to the I minus 1 divided by the sum of all those factors, which was about 90%. So for that first period, I have that 2% divided by that 0.9. That's going to be my weight to the most recent month's squared deviation from the mean. So let's go ahead and calculate the average squared deviations from the mean using this set of odd weights. And we'll just do it right here. This will be my weight. I'm going to weight last month 2%. Multiply that times the squared deviation from the mean. The mean on that month, make sure you don't get the excess returns. You go back and get the original returns. So there's the return on 1 month ago for capital 1 was 3.2%. I'm going to subtract that, and I just have the average of the returns there. I'm going to anchor row 31 here, and I'm going to square it. So notice I have here's just the average monthly returns of capital 1. So this formula here is the weight, 2.21%, times the return in 1 month ago, minus the mean, squared. Copy that down. Okay, so these are the square deviations from the mean using these unequal weights. If I take the average, if I sum up the square deviations from the mean, that would be the monthly variance. Right? If you sum up the problem, each weight times each square deviation of mean, that's giving you the monthly variance. However, I want the standard deviation, so I take the variance below. It's just the number below to the square root. Now this is the monthly standard deviation, and I multiply that times the square root of 12, and I get the annualized standard deviation. So let's take one more minute to look at this. EWMA, I start with 1 minus lambda times lambda to the I minus 1. I do that for all historical periods. I then sum all those numbers together. My final weight is the 1 minus lambda factor from the left divided by the sum. These weights add up to 100. Therefore, the capital 1's square deviation from the mean for the most recent month is that weight times the return in that month minus the average return over all months squared. If I sum up the square deviations from the mean times the probabilities, that is my monthly variance. I take the square root of that, that's my monthly standard deviation, but I want to annualize it and call it my annualized standard deviation. So AM 29 has my standard EWMA volatility for capital 1. So I'm going to put that over here. I think I said AM 29, so it's equals AM 29. That's my 34%. So how can I interpret this? Over the last 10 years, capital 1 averaged 31% volatility. They must be a little bit above average today, or more recently, because the EWMA volatility is giving me a higher number. It looks like volatility for all of these, the EWMA volatility seems to be higher for all of these. Actually, I was changed that lambda. Lambda I used was 0.98. Let's change that. So it looks like times are a little more volatile than they have been in the past for all these assets, since the EWMA volatility is greater than the simple equally weighted volatility. All right, so that is EWMA volatility. Where did I get the 0.98? Well, I stole it from JP Morgan's risk metrics technical document, which at one point was publicly available. And what this tells you is for US equities, the optimal lambda is 0.98. So how the heck would you get something like that? Well, think about this. What if you set up this scheme and you have, say, 10 years of data, and you keep taking, say, 1 year, 5 year subsamples. And what you do is you just find, well, what lambda is the best predictor of volatility the next month. And it just so happens for stocks, US equities, 0.98 over this period of time was the best lambda to predict. And I want to spend a little minute talking about, again, lambda again. Notice when lambda, I'm just going to go back to our spreadsheet area of the spreadsheet that has the EWMA. When lambda is 0.98, notice the first weight is about 2%, 1 minus lambda. Notice if I make lambda 0.95, notice the prior period's weight is 5%. If I make it 0.9, it's 10%. So the lower the lambda, the more you're weighting the more recent data and not weighting heavily the farther data. And let's try this. Try a lambda of 0.9999999. When I do that, notice the weights are about equal. And notice what solution it gives me. When you have the weights approaching 1, the EWMA vol approaches the long-term average. And if I were to make that, say, 0.9999 with, say, 10 nines, what you'll see is EWMA simply gives you the simple weighted average. So the lambda is just a constant. The higher the number, the more equal weight. The lower the lambda, the more highly you weight the more recent data. All right, so sometimes that lambda is called the decay factor. So I'm going to change this back to 0.98. And there we go. So that was estimating volatility using a simple sample standard deviation and EWMA. Next topic, we're going to look at Black-Scholes implied volatilities.